All right, chemists, let's get started. Last week we discussed effective nuclear charge. So for the majority of you that this is a new topic, let's get started. Yes. All right, so effective nuclear charge, this is what electrons, I guess, feel in terms of attractions to the nucleus. So if we keep track of what is the charge of our nucleus, how many inner core electrons are shielding that electron of interest from the full positive charge of the nucleus, we can calculate effective nuclear charge. This concept will come up when helping us predict different trends like size, ionization energy, and electron affinity, which we will cover today. And so basically the two things to keep in mind when looking at these different trends are, okay, what is the effective nuclear charge of that valence electron that we're trying to remove, or we're trying to determine its size. So keep track of effective nuclear charge, or Z effective, and the N value, so the energy level of that element. So in this case, it's its period row. So like N equals 1, 2, 3, 4. We want to know how far on average are those electrons from the nucleus. And so do remember that with Z effective, typically kind of our quick and dirty way of how we can determine the Z effective of a valence electron is it's simply the group number if it's a main group element. So that is the positive charge that that element or that electron feels in terms of its attraction towards the nucleus. All right, so keep in mind those things. We're going to be thinking about these three criteria for all of these trends: the N value, the Z effective, and then finally any additional repulsion from electrons if that substance, if that anion or cation, if it's charged. So we'll consider these three things, and we'll keep referring back to it. So we're going to talk about size of atoms first. So there's two different trends, one either going left to right across the periodic table or top to bottom. So the first one here, going down a group, all right, as we go down a group, if we look at group 1A, like lithium, sodium, potassium, we know that those valence electrons go 2s, 3s, 4s. So what we see there is that the N quantum number is changing. All right, it's becoming larger. So when that N value becomes larger, what we see is that the atom on average also becomes larger because the N value is increasing. I feel like that is the more straightforward trend. When we go down a group, right, things get heavier, they're going to get bigger. But the reasoning is because the N value is increasing, all right, as we go down a group. So if we compare lithium and sodium, which atom is larger? Lithium or sodium? Sodium, because sodium is a 3s element while lithium would be a 2s element, so it's smaller. All right, so that one a little bit more clear. The second one is what is the trend going left to right across the periodic table. So size actually decreases going left to right across the periodic table, and it's because of the increase in effective nuclear charge. I will mention that this is not intuitive. You would think if we look at the periodic table, or if you go through sodium to argon, aren't our elements getting heavier going left to right? So you would assume, right, that if things get heavier, they get bigger. Like those kind of go together, but that's not what we see actually. When we go left to right across the periodic table in the same period, the atoms actually get smaller. And it's because we've already calculated the effective nuclear charge of valence electrons, and we know that it's equal to its group number. If we think about the effective nuclear charge on sodium, it's +1, versus the effective nuclear charge on chlorine. What is Z effective on chlorine? 7. If you're an electron, are you more attracted to a +1 or a +7? 7, right. If you were a negatively charged electron, you will be more attracted to a +7 charge, so you're going to be on average closer to the nucleus. So what we see is that elements with higher Z effectives of those valence electrons are actually smaller. That is counterintuitive. It's counterintuitive. All right, so the first one here, the N value, that one makes sense, but what's counterintuitive is the left to right across the periodic table. So what we see here, and it's just repeating everything I just said, Here you see clearly going down group 1, the atoms get larger. Right, you see that? They get larger going from, lithium all the way to cesium. But then left to right across our periods, they actually get smaller, which is weird. Again, because if we look at the molar masses, these elements are getting heavier, but they're getting heavier and they're getting smaller in terms of, where to find electron density, that these atoms are smaller in terms of where we can find those electrons. And again, I have the explanation here. It's because going left to right across the periodic table, Z effective increases. So those valence electrons feel a higher attraction to the nucleus. So when you have a higher Z effective, they're closer to the nucleus because there's that higher attraction. So what we see is that these elements, like group 7 elements, they will be smaller because there's more attraction there. So let's go over this. Let's compare the effective nuclear charge on valence electrons on carbon and fluorine. What are those Z effectives? Do the quick and dirty way. What's the effective nuclear charge on carbon? What question should you ask yourself? Group number. So carbon Z effective is 4. I like to put +4 to really reinforce that it is a positive charge that those electrons are being attracted towards. Okay, and then fluorine, what is its Z effective? +7. All right. So if you are an electron, which is negatively charged, in which scenario, which atom are you more attracted? The fluorine or the carbon? The fluorine. So then which one's smaller? Fluorine, yes, because those electrons are more attracted to the higher Z effective. And so what we see is that fluorine is in fact heavier than carbon, but it is smaller again because of that Z effective. And so we can check our work here. See, this is the, I think this is in picometers. That's the radius of carbon, and then there's the radius of fluorine. So it's a little bit smaller there. All right. And again, that's the one that's not as intuitive. Okay, so everyone's favorite. Okay, so the examples I just gave is for what I call the main group elements, so the S and P block elements, where we have groups 1 through 8, easier to predict. As always, not as easy to predict is transition metals, okay? So transition metals, if we go across a period on the periodic table and look at the sizes of transition metals, so let's just look at those 3D elements. So what we see first, if we look here at this graph, all right, these green dots, these are our transition metals. So what we see as we go from potassium to calcium, we see that the size decreases. We know that's supposed to happen because we're going left to right. But as we continue going left to right, and now we enter the D block metals, the size still decreases till a certain point. All right, until we get to the end of the D block, then the size actually starts to increase a little bit. And then once we get back to the P block, then it continues decreasing again. So again, remember, D transition metals, harder to predict. And so kind of the exception here is towards the end of the D block. So towards cobalt, nickel, copper, zinc, the size tends to increase a little bit, and then it starts decreasing again. And the reasoning, all right, is once we are just partially filling that D block, the whole idea of effective nuclear charge still applies here. That as we are going left to right across the periodic table, we're adding an electron and a proton. So Z increases, but our shielding doesn't increase. So what we see as we go left to right, Z effective is what draws those electrons a little bit closer to the nucleus, so the atom gets smaller. But that is only true until around 6 or 7 D electrons. So once we start getting to 8, 9, 10 D electrons, something else takes over. It's electron repulsions. You now have 8, 9, 10 electrons in a small space, right? Electrons are negatively charged. So if you have a bunch of electrons close to one another in a space, what type of force is kind of occurring there? If there's a lot of electrons in a small space, repulsion. So towards the end of the block, we kind of see the atoms get a little bit bigger, and then it goes back to normal. Yeah, question? Yeah, it would just be the 2. Yeah. Yes, good question. All right, so let's put it all together. So we see, here's the graph kind of showcasing the trends that we see. So let's look at the big jump in size between argon and potassium. So it might help if you look at where argon and potassium are on the periodic table. So we see that potassium is much, much bigger than argon. What explains that difference? A difference in N or a difference in Z effective? That explains that difference. N, yes. So potassium is so much bigger because let's look at it. Potassium, its valence electron is N equals 4. Is it 4? N equals 4. And then the N value for a valence electron on argon is what? 3. Yes, N equals 3. So we see 4 is bigger than 3, so those N equals 4 electrons are going to be, on average, further from the nucleus. So that's why potassium is much larger. Okay, what explains the gradual decrease in size from sodium to argon? So this way. So it might be helpful if you look at where those elements are on the periodic table, going from sodium to argon. What explains that decrease in size, N or Z effective? Z effective, yes, and the idea here is that all of those elements are in the same N value, okay, so we can't, make a comparison on N value. So the next thing we look at if they're in the same N is to look at Z effective, and you'll constantly be doing that in this chapter. All right. And then finally, I already have these written in here for you. So kind of in that same reason, going from sodium to argon, this decrease is explained by Z effective. So for that same reason, when we look at the D block elements, all right, kind of the beginning here, D1 to D7, we see that gradual decrease, and that's because of Z effective. It's increasing going to left to right. But then the slight increase at the end is explained by electron repulsion. So that's kind of putting the exceptions together. So you should know these first two examples really, really well when trying to compare sizes of atoms. All right, so there we go. Okay, so that takes care of the first two criteria. Back in this slide, we're going to be exploring these three, N value, Z effective, and finally charge of the ion. So let's think about what happens in terms of size when things are charged. All right. So how do you make a cation? How do you make a cation? Yeah. You what? You remove an electron. Yes. So with that in mind, remember, the size of these atoms is based upon where to find electrons. So if you remove an electron, how do you predict the size will change? If there's less electrons. It's going to be smaller, right? Because we're removing electrons of, the electrons are what are defining the size. So there's just less of them, so they're going to occupy less space. The real reason is because if we remove an electron, we remove repulsion. And so essentially there's going to be more contraction that happens because there are less electrons being attracted by the same nucleus. So the rule here is that cations are always smaller than the neutral atom. And I like to just think because there are less electrons there, right? Remember, electrons is what defines the size of this atom. All right, there we go. And so the size of the cation decreases as the charge decreases. Again, because, iron 3+ has 3 less electrons, while iron 2+ only has 2 less electrons. So our size here, iron 3+ would be the smallest because it has the least amount of electrons. All right, good. All right, so then just imagine, okay, kind of predict what's going to happen here. What about anions? How do we make an anion? You add an electron, all right? So if our size of our atom is dictated by where we find electrons, if you shove more of them in there, it's going to get bigger. There's more electrons there. But the real reason is because if you add an electron, remember what we said when we have a ton of electrons in the same space, what kind of force is happening? Repulsions. So if you add more electrons, you add more things that are going to repel one another. It's going to expand, take up a little bit more space to take care of that repulsion. So anions are always larger than their neutral counterparts, right? And yeah, there's the reason. So same idea. Electron, we're adding. When we add that electron, we're also adding more electron repulsion, so the whole atom gets bigger there. So size of anion increases as negative charge increases. So our crocodiles should go this way. right? Is that right? Yes. Good. All right, so are we gonna do examples here? Nope, okay, one more. So those are cations, anions. There's one more thing to compare. All right, and that is an isoelectronic series. We already mentioned isoelectronic a little bit before. Isoelectronic just means same number of electrons. So we have an example here of a bunch of different particles. What makes them all similar is that they all have the same electron configuration. If you go ahead and figure out what they are, or the electron configuration for these, you will see that they're all the same. They all have 10 electrons total. They all have the electron configuration of neon. So 10 valence electrons. So there's something special that we consider when we're looking at when we're looking at particles that are isoelectronic, when they have the same number of electrons. We consider, well, what makes them different? So I already said all of these have the same number of electrons, but how do they differ? They're different elements, so therefore they have different number of protons, yes. So this is what you want to think about, okay? You are those 10 electrons. You want to think about constantly, what type of attraction do I have to the nucleus? So if we look through these elements, so the first one is oxygen here, has how many protons? 8. So the nucleus has a +8 attraction. Fluorine here has a +9 attraction. Sodium has a +11. Magnesium is +12, plus 13 for aluminum. So the idea here is that all of these atoms have this, or particles have the same number of electrons. So in which scenario, which nucleus is going to attract those 10 electrons the most? The one with the most protons, right? So which element is going to be the smallest? Or sorry, which particle is going to be the smallest? Aluminum, because same number of electrons, but a highly charged nucleus is going to bring those 10 electrons in closer, because they're just more attracted. So in this case, aluminum is going to be smallest, and then our oxygen anion is going to be the largest. All right, it's going to be the largest because it has the least positive nuclear charge. So those 10 electrons basically aren't as attracted to a +8 than it is a +13. Good? All right. Okay, next, are we going to do, yes, all right. So let's put it all together. Put it all together. Think about the criteria. We want to think about be thinking about, so I guess in this last example, the isoelectronic series, what we were doing, comparing the attraction of those 10 electrons to the Z, all right, so the positive charge of the nucleus, we were essentially calculating Z effective there. That there's a higher effective nuclear charge for the aluminum 3+ cation, all right, aluminum 3+, then is the O2-, that there's a higher Z effective for aluminum 3+. All right, so basically we're using that criteria, the second criteria here, to determine size, because I want us to pick the larger atom or ion in these different pairs, but I also want us to think about the reason. These are the reasons that I want you to consider. And they kind of happen in the order in which you should, I guess, refer to them. So the first one here are, our different reasons is the N value. If your N value is higher, that atom's going to be on average larger because the electrons are spending on average more time further from the nucleus. We also look at Z effective, so the attraction of those valence electrons to the nucleus, and finally more or less electron of repulsion if the atom becomes charged. So let's go through this. Let's look at oxygen and carbon. So I would locate them on the periodic table. Okay. Ask yourself, are the N values different? No, they're the same. All right, so if they're the same, that means we can't use the N value to determine the size difference. So what do we look at next? What criteria do we look at next? Z effective, effective nuclear charge. So what's the effective nuclear charge of oxygen? +6, and carbon is +4. So in what scenario, in what atom will the electrons be, what are we doing? The larger atom. So we want, which one are the electrons not as attracted to the nucleus? So in which one? What? Carbon, yes, carbon is the larger one because Z effective is smaller. So those valence electrons are not as attracted. All right, next one. Arsenic and what's SB? My favorite. Antimony, yay. All right, so just locate those on the periodic table. And the first question I ask, are they the same N or different N's? Different, yay, then it's easy. Which one's bigger? Antimony, yes, because antimony is N equals, I don't even know, 2, 3, 4, 5. N equals 5. And arsenic is in N equals 4. So we say antimony is larger. Right? We only can do that because the N values are different. In the previous one, the N values were the same, so we have to go to the next step. All right, next, potassium and calcium. Which one's bigger? Potassium, why? Z effective, and so we went to Z effective because potassium and calcium are in the same N value, the same energy value, so the next criteria is Z effective. All right, next, nickel and nickel 2+. The nickel, yes, which one? The regular neutral one, yes. And the idea, what's the reasoning here? Is it Z effective? Yeah, there's the electron repulsion. So in this case, there's, I guess, more electron repulsion in the larger one here, all right? Because when we remove electrons, we automatically make it smaller, all right? Versus the next one, fluorine and fluoride, which one's bigger? Fluoride, the F-, again, because adding electrons adds more electron repulsion and makes it bigger. Good. All right, and then the last one here, K+ and Cl-. So right off the bat, you might be looking at these and think, oh, K is N equals 4, Cl is N equals 3. So at first glance, you might say, oh, K+ is bigger. But that's not right. K+ and Cl- fall under a different category. How else are they, I guess, similar? We just talked about it. The same number of electrons. See how these aren't neutral atoms. They're charged, all right? So we can't use our N comparison here because these things are charged. So the idea here is K+ has how many? 18 electrons. Cl- also has 18 electrons. So what criteria do we think about to figure out the size difference? If they both have 18 electrons. They both have 18 electrons. They're isoelectronic, so we look at the charge of the nucleus, all right? So essentially, we're comparing their Z effectives here. So what's the charge of the nucleus on potassium? 19, and chlorine, 17, all right? So if you're just a stupid little electron that's negatively charged, which one are you more attracted to, or I guess in this case, less attracted to, because we're looking for the larger atom. Chlorine, yeah, so well, in this case, it's chloride is the larger one because you are less attracted to a +17 versus a +19, right? So that puts it all together in terms of size. So we will constantly be referring back to this. N value, Z effective, and then extra electron or extra or removed electron repulsion. These ideas will come up. All right, do we feel good about these? Good, all right. So let's go on to the next trend here, which is ionization energy. So this energy is the energy to remove an electron. So we're forming cations here, all right? So when we remove electrons, we always remove valence electrons because they are the most easily removed. They are on the outside of the atom, so it's easier because they're on the outside to just pluck them off. All right, but typically here, it always takes energy. It's always endothermic. It requires energy to remove these electrons from our atoms. So there's a couple trends here. So just remember, it's the energy to remove an electron. So if we write the actual equation that's happening here, think about, okay, how do we form a sodium cation? We take sodium in the gas phase, and we remove an electron, so therefore we make that cation. So we see here, when we remove an electron, the electron's a product. So this requires energy. This value, which oftentimes they just use I, is going to be a positive value. It will be in the unit of kilojoules per mole. You can look this up. We could also, in theory, remove an additional electron, all right, from sodium within here. So if, this is the energy to remove the first electron. Here is the energy to remove the second electron. So see how the product here is sodium 2+. In this case, because we've removed a second electron. So this value will also be endothermic. It's going to take much more energy to remove this second electron. It will also be in the unit of kilojoules per mole. So note here, this is this first line. We call this the first ionization energy of an element. This second one is the second ionization energy of an element. So note here, we take electrons off one at a time. So if we're thinking about that second ionization energy of sodium, we're not taking off those two electrons at the same time. We're taking them off one at a time. So do keep that in mind. All right, so I don't actually have values for these ionization energies. They all start with the element in the gas phase. That's the important thing. So to write these equations for ionization energy, it's always how much energy does it take to remove an electron from the atom in the gas phase. That's kind of the definition of ionization energy. I was gonna fix this slide, but I forgot to. All right, so always endothermic. So our trends actually relate directly to, what equation is this? Potential energy, or when we think about it, electrostatic attraction, same thing. So we see here the top is Q1, Q2, so that's kind of like the attraction that the electron has to the nucleus, and D, the distance, is how far away is that electron from the nucleus. So this is where the trend is. Think about it. If we have an atom and we have like an electron orbiting it, is it gonna be hard or easy to remove an electron if Z effective is a really large number? Is it easy or hard if that electron experiences a high Z effective? Meaning is it highly attracted to the nucleus? Yes, it's highly attracted. Is it going to be easy or hard to remove that electron? Hard, yeah. The more attracted the electron is to the nucleus, the harder it is to remove. So that's kind of what the top part of the equation reminds you of, okay? So more attraction, harder to remove. The denominator here, D, represents distance, how far away that electron is from the nucleus. So think about it. If your electron is far away from the nucleus, is it gonna be easy or hard to just pluck it off? Easy, versus if that electron is real close to the nucleus, okay, real close, okay, negative charge, positive charge. Is it gonna be easy or hard to pluck that off? Really hard. So a small distance means really difficult to remove that electron. So those are the trends that we see here. Ionization energy decreases going down a group because of N. When N increases, electrons become further away. All right, so essentially that's where this D, the distance term comes into play, okay? Because we know as N increases, distance increases, so it becomes easier to remove that electron. On the other hand, ionization energy actually increases going left to right. And again, it's because of Z effective. And if you forget, it's the top part of our potential energy thing that kind of reminds you of that here. The more attracted that electron is to the nucleus, the harder it is to remove. So that's why ionization energy increases going left to right. All right, so we kind of see that trend here. As our things go left to right, we see ionization energy gradually increase. When we jump to the next N value, because the atom's getting bigger, it drops down. But then it starts going back up again because we're moving left to right. You see that there's some zigzags here, and that's where our exceptions occur. So there are some exceptions between 2A and 3A elements, and 5A and 6A elements. So you can see that's where these are. So like right here, lithium, this would be beryllium and boron. And then this one, this next little blip would be nitrogen and oxygen. So what we see is that oxygen and boron don't fit this, it's not a straight curve. What we see is that boron and oxygen have slightly less ionization energies than typical. So I have the electron configurations here, and you just think to yourself, if you are an electron plucker, think about in which scenario is it easier to pluck off an electron. Remember, electrons have spin. So here we have beryllium, and then here we have boron, so there's an extra p electron. So in which scenario would it be easier to pluck off an electron? In the beryllium or boron case? Boron. Which electron? The p, the one that's spinning all alone. The one that's all alone is going to be much easier to just pluck off. So this one's easier to remove. Versus in beryllium, see how everything's paired? Everything has a partner, so they kind of get a little stability hugging one another because they're all spinning oppositely, all nicely. So it's harder to remove these electrons because they're essentially hugging one another. And so that's what we see here. See, if we go back to this graph, we see that boron, it's just slightly easier to remove that one electron because it's spinning all alone. All right, and these are first ionization energies, by the way. All right, we see kind of a similar thing for nitrogen and oxygen. So here are those electron configurations. Which electron is easier to remove, the easiest to remove? Is it in nitrogen or oxygen? Oxygen. Which electron? Yeah, the one that's spinning in the different direction than everything else, all right? So it's kind of like the oddball, okay? And I guess in these cases, the oddballs are just easier to pluck off, you know, like a pack of chickens. I don't know, I keep thinking about chickens. You know, if you have like a chicken that's kind of off doing its own thing, it's more likely to get, you know, yeah. Okay, so just like that. So this one is easier to remove because it's different. And so that's what we see here. See how oxygen's just like a little slightly lower than the nitrogen counterpart. Remember, when we have a completely half-filled subshell, we get a little extra stability. So this is a little bit more stable than predicted because everything is spinning in the correct direction, happily half-filled. Yeah. We won't, yes, it will be the same for d orbitals, but don't focus on the d orbitals as much. Yes, okay, so those are ionization energies. Okay, so I mentioned, up here. Okay, so this is the ionization energy for the first electron on sodium. What about, note this second reaction that I wrote. Do you think this will happen? No, why? Why do you not think this reaction will happen? Yeah, sodium 2+, that doesn't happen. Sodium typically forms what charged cation? +1 because it is a or a 1A element. So this second electron is not likely to come off. So that's kind of why I wrote 2+ signs. It's a really, really large number. All right, and so the idea here is with successive ionization energies, we can look at, okay, how much energy does it take to remove one electron at a time? All right, so as we're removing electrons, the positive charge of the whole particle is increasing. So with these successive ionization charts that we see here, this is the energy to remove the first electron in sodium. Here is the energy to remove the second electron in sodium. So see how huge that number is? So the idea is you need to spend a lot of, you know, kilojoule energy, money, to take that second electron off. So is it likely that that will happen? No. Versus for sodium, the first one, it's fairly easy to take that first one off. That's why sodium can commonly be found as a +1 cation. It's never going to be found as a +2 cation because of energy. It literally just costs too much thermodynamic energy to take that second electron off. Same thing for magnesium. Can you tell by the numbers what type of cation magnesium can be found as? Can you tell by the numbers? See, in sodium, there's a huge jump between 1 and 2, meaning that it loses 1 electron easily, but not 2 electrons. So for magnesium, how many electrons can it lose easily? 2. Is that consistent with what we see for magnesium? Yes, that third electron is super duper hard to remove, so it's not going to be removed in nature. And you see the same thing for aluminum. How many small numbers should you expect? 3, and that's exactly what we see. All right, that fourth electron, it takes way too much energy to remove that fourth electron. So another thing to note here, see how for aluminum the numbers increase a little bit each time? We won't ever see a decrease in ionization energy. Like if we go from like 1, 2 to 3, it will never dip. All right, because the idea here is we're making a more highly charged cation. It always takes more energy to remove an electron from something that's already positively charged. So we'll never see a dip in energy. It'll always like gradually go up, and then you'll see a big jump, and that's how you can tell how many valence electrons there are. All right, so there we go. So yeah, that's what I meant here in general. The first one's always the easiest. The second one's a little bit harder. The third one's a little bit harder within there. And so, you know, these charts are explaining finally, you know, why in chapter 2 I told you to memorize, you know, aluminum always forms a 3+ cation. This is why. This is why. The reasoning, it's not arbitrary. It's all because of energy in chapter 5 concepts. Or the idea that lithium and sodium, they always form +1 cations. It's because energetically it is favorable to do that. It doesn't cost that much energy to form these cations. All right. And in general, right, that the idea here is that losing these electrons, these are losing valence electrons. Valence electrons are the easiest to remove because they're the furthest away. All right, so let's keep going. Okay, so these are common exam questions involving ionization energy. All right, so let's look at the first one. What is the chemical equation describing the third ionization energy of aluminum? A, B, or C? What was the trick, the hint I gave you for successive ionization energy? It's the energy to remove an electron, one at a time. So if you were to get this question wrong, you would probably say B, right? B, where you just take off all 3 at the same time. But no, that's not what ionization energy is. It's what is the energy to remove the third electron. So in order to get the third electron, you might have to write the others, right? The first and the second, to figure out, okay, what is the reactant to in order for us to remove that third electron. A is not right because this isn't balanced. See how the charges are not balanced? That one side is neutral, the other one's not. So that one could also be a mistake there, but remember, it has to be neutral. B is neutral, but this is not the ionization energy. See how a +3, -3, that makes it neutral on both sides. So the idea here is that the first ionization energy for aluminum will be aluminum to make aluminum plus that first electron. And then what you do to do the second ionization energy is that you take the product from the previous line. So we take aluminum plus, and now we remove a second electron. What's our product here in order to make it all balanced? +2, 2+, yes. And then so now this is our third ionization energy. This is what we want. So we take the product from the previous step, and we're removing our third electron. So what's the product there? Al3+. So that is the correct answer. C is our correct answer. Good. And so if you were to get this wrong, and again, because it's the concept of successive ionization energy might not get there, you might say B. But we don't take off all 3 electrons at the same time. It's one at a time. Okay. Of these 3 equations that I wrote, which one requires the most energy? 1, 2, or 3? 3. The third ionization will cost me the most energy. And the idea is I'm taking an electron off of something that's already highly charged. Okay, so something that's highly charged, we're removing something that's negatively charged. That's not going to be super favorable. So it's going to cost me a lot of energy money. All right, here's the second one. Okay, what second row element could possess this successive ionization energy? What does this graph show us? The what? How did you get 4 valence electrons from this graph? Okay, so they said that the energy jumps after 4. Or we can think about that the first 4 electrons, they are easily removed. It doesn't cost me that much energy, or too much energy to do that. So this picture is implying that there are 4 valence electrons. Do you agree with me? Okay, so now how do we figure out what element it is? Yeah, so it's 4 valence electrons, and I tell you it's a row 2, n equals 2. So now you just look for what n equals 2 element has 4 valence electrons. What is it? That's not n equals 2. Carbon, yes, this would be carbon. All right, because if we write out the electron configuration of carbon, it's helium 2s2, 2p2. All right, now this is a chapter 6 question, right? If I gave you that electron configuration and I ask you how many valence electrons does this have, you would say 4. And those 4 valence electrons are in what n value? 2. And that's exactly what this question's asking. Good. Okay. So now we're relating the new concept of ionization energy, successive ionizations to valence electrons, these electron configurations. All right. Last question. All right. Okay. Consider these 3 elements: sodium, calcium, and sulfur. All right. So here I'll just write them quickly. So we have what is this? Sodium. We have calcium and sulfur. Which has the largest first ionization energy? So which one takes the most energy to remove an electron? So remember, look at size. Size will help. So if we're looking at size and ionization energy here, what kind of, is it going to be easy or hard to remove an electron from a really big atom? Easy. If it's a really small atom, is it easy or hard to remove an electron? Hard, yeah. It's that atom is like hoarding the electrons like a dragon, all right? It's just holding them. It's going to be real hard to take one out when it's just like laying on them. But when it's really, really big and fluffy, right, it's going to be easy to just pluck an electron off. They won't even notice when it's far away. Okay, so in this example, if we look at size, okay? So when we look at size, what criteria do we think about? N and Z effective. So will calcium be the smallest? No, it's going to either be sodium or sulfur because that's N equals 3, all right? Sodium and sulfur is N equals 3. So it's one of those. How do we differentiate between within N equals 3? Next, we look at Z effective. So think about the Z effective. For sodium, it's +1. For sulfur, it's +6. So in what scenario is the electron going to be more difficult to rip off? Sulfur, yes, it's sulfur. Because it's basically because it's the smallest. Okay. Okay, so, or I guess this shouldn't say look at size. It should be look at Z effective. That's really what it should say. Okay. All right, what is the largest second ionization energy? So this is the energy to remove the second electron. What do we think? Sodium? How'd you get sodium? So if we think about it, we already kind of looked at it. For sodium, the first electron is going to be fairly easy, but the second electron is going to be hard. Why do we know it's going to be hard? That's an inner core electron, right? That's not a valence electron anymore. So in this example, sodium only has 1 valence electron, so it's going to have the largest second, because now we kind of went inside the inner core. So note here that calcium has 2 valence electrons, sulfur has 6. So you'll see, fairly low numbers for the first 2 in calcium and the first 6 in sulfur. So that's why we know that for the second ionization energy for sodium will be the largest. All right, see how we put it all together? Good. All right, so that's the second trend. All right, let's look at the last one, and that's electron affinity. So we took off electrons to make cations. What do you think we're going to do next? Add electrons, right? This electron affinity is the energy associated with adding an electron to an atom, forming an anion. So just like electron ionization energy, with electron affinity, there can be a first, a second, a third. It's the energy to add the first electron, add the second electron, add the third electron. I will note here, thanks, Ms. Holton, that she taught that electron affinity in high school. My high school teacher taught me that electron affinity and electronegativity were the same thing. Did anyone else learn that? Or in your mind that they were when I say electronegativity, does that like ring a bell? Yeah, and for some reason, like I learned those two things together, but they're completely different, okay? So electron affinity, and remember, she messed me up for a long time. Electron affinity is an energy term, all right? It's a term you can look up and it has a kilojoule value associated with it. This is the energy you get or required to put an electron on something. It's an energy value. Electronegativity is a little bit different. We're gonna talk about it next chapter, all right? So that's the idea here. Okay, so if we think about it, for some atoms, it's actually favorable to add an electron. We know that chlorine typically forms a chloride minus anion, chloride. So this happens because it's actually energetically favorable. It's exothermic to add an electron on a neutral chlorine atom. So this chloride is actually very stable. Versus try to put an electron on argon. Argon's a noble gas. It doesn't react. It's not going to add or gain electrons because it's unfavorable to do so. Its electron affinity is unfavorable. It's endothermic. It would actually require you to put energy into the system to make that happen. So it's probably not going to actually be seen. So how we predict electron affinity, it's the same idea. We use the same equation. Think about how attracted is that electron you're adding to the atom. So look at the valence electrons that are currently on the atom, because we're thinking about, okay, you're going to put an electron on that atom. How attracted is it going to be to the nucleus? The more attracted that added electron is to the nucleus, the more exothermic it will be. It's the more negative the electron affinity will be. Remember, negative in terms of energy is good here, that it's exothermic. We want to put electrons on atoms to form these anions. So it's only the first electron affinity is typically exothermic, a negative value. Second and third electron affinities are always positive values, because if you think about it, like chloride minus, if we want to put in another electron on that, chloride is already negatively charged. So trying to put an electron on something that's negatively charged, that's repulsion. So you need to put energy into the system to make that happen. So it's a positive value endothermic for the second ionization energy. We only see negative numbers like you see here for the first ionization energy. So basically what you want to think about is, okay, how attracted, so that's Q1, Q2, is that electron to the nucleus, and then how close are you putting that electron to the nucleus? So essentially, you are considering, okay, what's the Z effective, right? If we have a high Z effective, then the added electron is going to be really attracted to the nucleus. Then we look at D, or the distance. If the atom is already small, then that added electron is going to be really close to the nucleus. And so again, that factor will also give you a lot of energy at the end here. So here are the trends. As size decreases, electron affinity gets more negative, but as Z effective increases, electron affinity becomes more negative. Again, remember, more negative means more exothermic, more favorable to do that. So here are some exceptions. Noble gases always requires energy to put electrons on it because they're already stable. The same kind of idea for alkaline earth metals. So all of these elements, the added electron will open up a new 2p or like a p subshell, so that's not super favorable. So we typically see positive values. Group 5A, similar to ionization energy, this is reasonably stable, so adding an electron, we would have to put its spin down. It actually costs us a little bit more energy, or we get less energy back than typical for group 5A elements. And then last here, we would predict, because fluorine is our smallest atom, that it would have the most negative electron affinity, but we actually don't see that. We see chlorine actually has the highest electron affinity. The reason that fluorine here isn't more negative than this number, because we see the trend here, it's kind of weird. We would expect this to be like negative 400, but it's not. It's because fluorine is really, really, really small, right? So if we add an electron, we're filling up that 2p subshell. But because 2p is already so small, you're shoving 6 electrons into a small space. What happens when you put a lot of electrons in the same space? What force is there? repulsion, so that's why we get less energy than typical for fluorine. And so that's just a small exception. That's an exception that comes up often, though, I would say, on exams. That one. All right. And then again, second, electron affinities are always unfavorable because the thing's already negative. So let's put it all together and see if we can't do this. All right, remember, think about how attracted is your electron to the nucleus and what is, how close are you bringing that electron in, so the N, all right? So the larger, what are we doing? Which atom is predicted to have the larger magnitude of electron affinity? So meaning, in which atom is it more favorable to put an electron? That's what I mean by it. So I'm looking for which is the more negative number, all right? So the first one, what is it? Lithium versus sodium. In which scenario do we get more energy out to put an electron on, lithium or sodium? Why? Well, yeah, but why? It's smaller, yes. Lithium is smaller. Think about it. The electron we're putting on lithium is going to an N equals 2 versus on sodium it's going into an N equals 3. So in which atom are we bringing the electron closer to the nucleus? Lithium. So we're going to get more energy back. So the answer is lithium. And the reason is N. Because in this example, lithium and sodium are the same Z effective. All right? So you can think about, the numerator is the same, but the denominators are different. Okay, aluminum and silicon. Which one will you get more energy back by putting an electron on it? Remember, we think about N value, we think about Z effective. In which way, which scenario, will that added electron be more attracted? Silicon, because aluminum they're in the same N value, so N equals 3. So we look at Z effective, so aluminum is +3, silicon's +4. If you were an electron zipping around, are you more attracted to +3 or +4? +4, so you will spit out more energy, okay, when you become attached to a +3. So in this case, it's Z effective. All right, chlorine versus chloride. Which one is it more favorable to put an electron on? Chlorine, which one? Neutral or minus? Neutral, and the idea here is chloride is already negative. It's already negative. So you're trying to take a negative particle and shove a negative electron on it. That's not super favorable to do. All right, the next one, calcium versus calcium 2+. Remember, you're just a stupid little electron. What are you more attracted towards? +2. Aren't you more attracted to +2 than neutral? Yeah, so in this case, it's more favorable to be an electron, add an electron onto calcium 2+. Good? All right, and so I guess the reasoning here is more attraction? More attraction? I guess that's the reason? Okay. I will say electron affinity is the harder of, I think, all of the trends. I think it's the hardest. It's the energy, again, I say associated with adding an electron, because sometimes it's a positive number, sometimes it's a negative number. So that one's a little bit more iffy versus ionization energy is always a positive number. All right, so, okay, we got 2 minutes. Oh, okay, yeah, so putting all of this together, we should be able to get the electron configuration of ions, all right? Because think about making ions is just applying the knowledge of ionization energy to form cations or electron affinity to form anions. So the idea here, remember from chapter 2, anion charge, all right, was always group number -8, that we would add electrons in order to get to the noble gas configuration. And really the reasoning is because it is favorable in terms of electron affinity to do so. So if we kind of write out these new electron affinities electron configurations for these substances. So for fluoride, we add an electron to fluorine. So where do you think we add that electron? To 2p, and so this becomes 2p6 in order to make fluoride. But for S2-, we add 2 electrons, so we fill out 3p6, so 2 electrons there as well. And again, we add those 2 electrons, or these electrons in these examples because of the electron affinity, that it's favorable to do so. Easier to see how we remove electrons. Remember our rule, cation charge is group number. So for potassium, you can clearly see how many electrons is it most favorable to remove. Just one. So that's why we see that K plus has a noble gas configuration of argon, versus magnesium will lose 2 because, again, small ionization energies there. So it'll only have neon. And so the last one here, gallium, falls under one of the examples of like a variable charge cation. Germanium, oftentimes we have to use the stock system, and this is the reasoning why. Gallium plus and gallium 3 plus exist. What electron do you think we lose is easiest to remove to form a gallium plus? Which electron is removed? The 4p, see how it's all alone? So it would be, you know, argon, 4s2, 3d10. But you see how we can also make a gallium 3 plus? We would remove those last 2 electrons, all right there, and just have 3d10 within there. And again, the first electron is fairly easy to lose to make that gallium plus, but if there's a little bit more extra energy in the system, we can lose that last 2 to make gallium 3 plus. All right, so there we go. And we'll talk about weird exceptions for transition metals on Wednesday. We'll finish up chapter 7 and start chapter 8 on Wednesday.